This lecture is a continuation about how to analyze an algorithm. We talked about different kinds of speed of algorithms, but in this one, we're going to see how we find that out. If we don't know anything about the algorithm, how do we calculate the speed of it? So, once again, what is a good algorithm? The kind of two questions you ask yourself: how long will my program take? And why does the program run out of memory? We'll focus on the first one about the speed of the program. So, we talked now about the scientific method. We'll observe the algorithm. So there's some algorithm, we'll see how it runs. Then from our observation, we'll make a hypothesis. Then we'll make a prediction, we'll verify, and we validate. So here are the orders of growth. There's constant, there's logarithmic, and here we have from the fastest to the slowest. Yeah, log n, n log n squared, n cubed. And you see here, this is just plotted between 0 and 10 for the n. And you see immediately that, exponential and the cubic are the most time consuming. So that's the amount of cost, amount of time it takes for something to go. So what if we're just given that graph and we don't know if they're a constant, log, or linear, cubic, quadratic? How do we work our way backwards? We use log transforms, use our log laws. And the two laws we use are the log law for multiplication. Log of a times b is log of a plus log of b. Similarly, log of a divided by b is log of a minus log of b. But this one is the most important one. Log of a to the power b is equal to b log a. So the power jumps down in front. Okay? Now, let's think of a simple example of the linear case. We have an algorithm, its cost is a1n. We actually don't know this. We want to find this out, but let's say we did. Before, what is the cost of the algorithm? Well, the constant doesn't matter. What's the most expensive thing is a to the n. a1 doesn't matter, it's just n1. But how do we find this out mathematically? What we do is, we take the log of it, and the log of n to the power 1, it's the same as log a1, which we don't care, it's just a constant, 1 times log n. So this one here is what we care about. And what this actually is the formula of a line. So that's a constant plus mx. X is log to the n. We're replacing it by log n. So what does this look like? For quadratic, it's very straightforward. If it's a quadratic of this form of cost, that's approximated by a2n squared or n squared. If we take the log of a2n, that can be rewritten using our log laws as log a2 plus 2 log n. And the 2 is what we're after. 2 is the order. So here we have the log form of a linear and quadratic. Here, this is what a quadratic formula looks like. You see the line is like this. A quadratic should look like this, but when you do the log transform, it becomes linear, it becomes a line. You take the log transform of any complicated function, any polynomial, and it becomes a line. So let's think about the cubic, which is just an extension. Polynomial of degree 3, that's what the 3 here is. So the order of this is n3. So if we rearrange our formula, take the log of a3n3, that's just log of a3, 3 times log of n. Yeah. So by taking the log of what we know, we actually immediately find out the slope of a line, which tells us our order. Okay. And so here's just an example of how order impacts. Here are 3 different cubics: n cubed plus n cubed plus n squared, and all this. There is a small difference early on, but then as n gets larger, the cube term dominates, and that's all that matters. And you note here, look at this line. That's x is equal to 1, x is equal to 2. When x is equal to 1, y is equal to 3, or that's a y is equal to 3, and y is equal to 6 when x is equal to 2. So what's the slope of this line? 6 minus 3 divided by 2 minus 1. The slope is 3. But what the slope of the log line is the power of the non-log. So the general form of this says you can have any polynomial, and if you take the log of it, you can find out what the power is, the largest power. So let's do a couple of examples. The linear example is the easiest. So here, what we have is an algorithm, and we tell it to do 16 operations, and it takes 74 milliseconds, we'll say. We tell it to do 64 operations, and it takes 266 seconds. We tell it to do 256 operations, and it takes 1034. And that's what this plot is. Plot 1, 2, 3. And actually, that just looks like a line, doesn't it? And while we don't know this, but that's actually what the answer is. We should never have access to that. If we knew the answer, there's no point doing any of this. Now, let's take the slope of this line. So that's its classic y2 minus y1, but y2 is tn2 minus tn1. So here we have slope of 4, slope of 4, slope of 4. Now that's the slope of our line. That doesn't tell us the power of the line. So we do the log transform. Now, here is the original, and here is just me taking the log of each part. So that's my original data. And now I convert it by taking the log of each of them. So log of 16, log to the base 2 is 16 is 4. Log to the base 74 is 6.2. And so we get all these numbers, yeah? And we have a new plot. So now this is the log transform version. And like before, we just find out the slope. Now the first is 0.93, 0.98, 0.99. So the slope is tending towards 1. Yeah, it's not perfectly 1 because there are the other elements impact. But what we have here is our slope is equal to 1. So that means we have our original slope, and then we have the slope that refers to the power. So we have 4n to the power 1. Yeah. Now, I told you earlier, and if you remember, the actual formula for this was 4n plus 10. Yeah, to the power 1. But we don't care about the 10. That's just constant. We just care about this part here. But what we actually care about is n to the power 1, and that tells the order. And that's this part of the information. The slope there gives us the answer. Yeah. So whatever that looks like it's heading towards is what it is. And so that's what we have here. The left side is the original. The cost is 4n plus 10. And the right side is the log form of it, which is the same as log 4 plus 10n. Yeah. Note, I use tilde because there is just a small little term that needs to be added in, but we don't care about that. Let's do the exact same, but for a quadratic. So here we have, once again, I'm telling you the answer. So the approximation of this is n squared. Yeah. So here we have our points. We tell it to do 1,024 operations, it takes that many. We tell it to do 4,096, it takes that many. We tell it to do 16,000, it takes that many. And as you see, this curve gets, it's not linear. If it was a line, it'd just go like that, but it is not linear, it's a quadratic. But you don't know that yet. So we take the slope at each point. So we have a slope of 10,000, slope of 46,000, and a slope of 164,000. Now, each of these are very far away from each other. So they're not equal to each other. So therefore, not linear. Yeah, it is not linear. Unlike in the earlier example, where you see actually every single slope was the same, and that would say it is linear. It's a line. So, not linear. So now we do our transformation. So we take all the original data and we take the log of each of them. So that's our new table on the right, the log transform of it. So we get our plot. Here's our new log data, and here's our plot. I chose nice values n, such as 10, 24, 40, but the right size up. And now you see this looks like a line. And when we take the slope of this line, you see that slowly, very quickly tending towards number 2. So that means the order of this is 2. It's n squared. We have our two things here. And that's tilde approximately 2, approximately 2, approximately 2. This here says it's not linear. This tells you that's squared. So.
I didn't get that. Could you try again?
So what we have on the left-hand side is the original. On the right-hand side of the log form, and it's squared. Yeah. Some other examples of this, you can do it for cubic. I'm not going to do the calculations. You'll do that in class. This is what the cubic function would look like, expanding. But the log transform looks like a line. And the line, like before, is a slope 3. Yeah, so you know it's cubic. And then when you get to higher powers, it gets much more difficult and much more involved. But you can do this kind of rule. That's how you analyze an algorithm. If you don't know anything about the algorithm, and you can just put in, tell me to do 100 version, 200, 300, and you can predict how long it would take to do 1 million and 2 million. And that's how you analyze an algorithm without knowing anything about the algorithm. So